So I have a question regarding the quiz. Isn't part B considered unsymmetrical bending when you calculate along the y-axis? It's still wait. It is unsymmetry. You're right, but at a certain y distance, the numbers are still the same. Okay. Far rules. Okay. What do I mean by that? If you move a certain like z distance, okay, the stresses on the left hand side and the right hand side, okay, so or the bottom and the top. So if part B is moment about y, right, is moment, so part B is moment about y, wait, yeah, moment about y. So if the structure is like this, I think our structure, I can't remember how our structure is look like, right? So it will go this way, right? Here and here, the values are still the same. Here and here, right? More if moment about moment about y. So stress x is equal to my over iyy multiplied by z. Sorry. So if this is the axis of yy, right? This is our yy. So the height over here, if we have a certain distance y over here, right? Sorry, z. So this is our z distance over here, right? Relative to this point over here, z value is still the same. Okay, so relative to this value, right? Let's say we draw a line down here. Up to here, the values are still the same. Okay, so that's why we still classify it as what? Symmetry. Okay, but the structure over here, there's nothing over here, so there's no stress. Okay, so we still classify it as sandwich material as symmetrical bending. Farus, is that clear?
Yes, got it. Thank you.
Okay, okay. So I know there's no material there. You will say, hey, there is material here. There's no material here. It should be no. Okay, because of the formula. If you look at the formula, you have z down here relative to the z distance over here. You still the stresses are still the same. Okay, so up and down. Okay, right. I need to write out the formula, then I can relate. Okay, so that is this topic. Okay, without that visualization is not easy. Now we're gonna look at sandwich material today, and then I hope to finish off with eccentric symmetrical bending. Okay. Now sandwich material, I'm going to teach both ways, two ways of loading, which we will use later on in eccentric symmetrical bending. So we are going to look at both bending. Okay, we're going to look at bending and also under axial loading. Okay, axial loading. So we're going to look at both axial loading. In fact, axial loading, we taught in the first 2 weeks. Okay, we taught in the first 2 weeks before shearing. So it's not a real difficult concept to understand axial, but I want you to derive the formula later on. Okay, now sandwich material. So what do we mean by sandwich material? Okay, sandwich material is a structure that is made of several materials. Okay, so several can be one. Oh no, one is not seven. It can be two, it can be three, it can be four, it can be whatever. Okay, but don't go over the top. Okay, the most I've seen is three. I'm not seeing four. Okay, manufacturing costs will go ridiculous. Okay, so the composite material, so we call sandwich material. Okay, sandwich materials is also known as composite material or known as composite beam. Okay, composite beam, right? That that are made of materials. It's the same thing like the previous statement that has. So if we use different material, means it has what? That has different Young's modulus. Okay, that you have that is made of different Young's modulus. So let me show you if it's made of a single structure, what is the formula like, okay, for bending moment, okay? So if we were to focus on bending moment, okay, so if the structure is made of a single material, right? So you guys know this formula so well now. So we will have stress X is equal to my over Iyy multiplied by Z, or mz over Izz, right, multiplied by y. Okay, so this is for a single material. Okay, so this is for a single material. Now, if it is a composite, okay, beam, or if the structure is made of several material, right, the formula changes, and it did not change ginormously, but all we have now is stress X, and we have a coefficient down here, okay, my over Iyy multiplied by Z, or again we have a coefficient. I can't remember what is the Greek symbol for it, okay, but it's written that way. And any student that has a Greek background can read Greek numericals or Greek alphabet, can you help me out? Anyone? I don't hear nothing. It's okay then, okay? So I call it so-called an N, okay, but I'd rather call it a coefficient. Okay. So you will see the difference, okay? All we need to do is to put an N down here, which is the coefficient, okay, where N right, is the coefficient of the reference material, okay, of the reference material. Okay, so let me tell you what this N actually does, okay? Okay, let me tell you what this N actually does, okay? So I'll draw now, okay? If you guys are copying and I'm moving, tell me to like, can I move back? I will do it, okay? I will shift I will not move the sheet of paper so quickly, okay? So if our original sandwich material, sorry, our original configuration looks like this. Of the sandwich material, okay? So I'm going to sketch this out now. So we have, and I want you to see relative to how many squares, okay? How many squares I'm drawing. So this one I'm going to draw 5 squares, okay? So the top material and the bottom material, okay, are 5 squares across, okay? And the center material is 4 cross. Okay, so we'll go. So the original one, okay, so this is our sandwich material. So the top is made of steel, The center part is made of brass, right? And the bottom part is made of steel, right? So if you were to look at steel, okay, the Young's modulus of steel is equal to 200 gigapascal. Okay, so if you look at textbook, is between 200 or 190 to 210. Okay, so for simplicity's sake, the Young's modulus of brass is about 103. I'm going to just say it's 100 gigapascal. Okay, I'm just, for this case, I'm going to say 100 gigapascal. Okay, so I'm going to generate two cases now. Okay, at the same time, while generating the two cases, I will write out the formula for for calculating the coefficient. Okay, so case number one, right? Our reference material is steel. Okay, we decide to use steel for our reference material. Okay, so the coefficient for steel, or the coefficient, now I'm going to write out the coefficient. Okay, so I'm going to write out over here. So the coefficient is equal to Young's modulus of the material divided by Young's modulus of the reference material. Okay, and the n down here will be the material. Okay, so that is the formula for it. So for this case, we want to find the n of steel, right? So we decide to take steel as the reference material. Okay, so reference material is steel. So n of steel is equal to Young's modulus of steel divided by Young's modulus of steel. Okay. So this is equal to 1. Okay. So now when we calculate the n of brass, is equal to Young's modulus of brass divided by Young's modulus of steel, right? So this is equal to 100 divided by 200 gigapascal. So this is equal to half. Yes or no? So geometrically, what does it actually mean? Okay, I think the more important thing to know is geometry. What does it actually means? So if I'm going to draw the geometry of steel, okay, because of the coefficient, the geometry of steel did not change at all. Okay, so this is 5. Right, this is 5. This is 5. Now, before I elaborate, okay, before I draw, when we say that the reference material is steel, means what? The brass section, we replace it into steel. I repeat again, the brass section we will replace with steel. Okay, so now this is steel, right? This is steel. So by using steel as a reference material, and it's because it is half, okay, what happens now is this. Watch, okay. So what happened now is I should not have it's okay, it's already done. So 2.5. Okay, so now this is brass, right? It's changed to become the equivalent to steel.